geometric series and sequences. So very similar idea. We're looking at patterns of either growth or you could call it decay, but things increasing or decreasing. And we have some pattern here of values. The difference between geometric and we just did arithmetic is arithmetic grows by either addition or subtraction, or I should say changes. This one changes by either multiplication or division. So when we take a look at this, I could check for arithmetic and go, hey, what's the difference here? Okay, we got a plus 25, but then I have a plus 120, so that's not the same. So which means this is not arithmetic. I never spelled this right. Something like that. But if we check for multiplication or division, if we divide the numbers, okay, and we divide the second one by the first one, so if you remember, we give ourselves term numbers. This would be T1, this would be T2, this would be T3, right? T1 is equal to 6, T2 is equal to 30, T3 is equal to 150. That's just a term number value. If I divide them, this is increasing, and because it's increasing, that means we have multiplication by a number greater than 1. We can technically multiply by numbers smaller than 1, which is kind of like essentially division. But if we multiply by 5, we go there. And then if we multiply by 5 again, we go there. So it looks like this is our pattern. In our formula here, it says the value of a specific term number is equal to A. A is the first term, which we actually have. So we know that our A is equal to 6, which is also considered term 1. Start writing that color there. R is the common ratio. So the common ratio here was our multiplying by 5, okay? If it was division, you would think your common ratio is, let's say it was divide by 5, we would say it's 1 over 5 if dividing, okay? So just keep that in mind. Division is a shrinking pattern and multiplication is our growing pattern. So with that being said, this is the formula to calculate the terms in the sequence. So we have 3 terms. Let's just go to the 5th term. It's an easy one for us to check. We can quickly multiply by 5 2 more times. In fact, let's do that right now just to see if we check. If we multiply that by 5, see if I can do this in my head. We go 0, 5, carry the 2, 750, and then 0, 2, 3, 7, 5, 0. I think that's right. So let's use this to calculate it. We're looking for our T5, our 5th term, and what's the value of it? Well, we're looking for T5, which means we take the very first term, which in this case happens to be 6, and then we have our common ratio, which is the number 5, to the power of whatever term we're looking for, which is the 5th term, minus 1. So that power there is 6 times 5 to the power of 4. 5 to the power of 4, you're going to have to help me. That's going to be 3 is 125. So like 7 something? I don't know. 725?
625.
625. Okay. 6 times 625. And what does that give us? 6 times 625.
3,750.
Good. All right. That means I did my math properly in the first one. So that gives us the value of that term. And with that, we could have also said, or they could have told us, hey, there's a value. There's a term that has a value of 750. Now we know it from up here, but we're just going to use this for checking purposes. The term number value is that what is n equal to? Well, we can set up our exact same formula again. We know that we have Tn is equal to the first term times the ratio to the power of whatever term we're looking for, subtract 1. We know this is 750, so we plug in 750. Our first term was the number 6. Our ratio happened to be 5. N is unknown, minus 1. So can we solve this piece? Well, we can do some isolation. We can divide both sides by 6 because this 6 is like a coefficient. That drops off. Here's a good question. What does that become? That becomes 1. 15 goes in 2 times 5. 125 is equal to 5 to the power of n minus 1. Okay, I could use logs to solve this. Another way I can use some quick algebra is, can I represent 125 as a base 5? So I can kind of run through some of my powers over here. I know that 5 to the power of 1, that's easy. 5 to the power of 2, that's not so bad. 5 to the power of 3, maybe I jump on a calculator. I happen to know it off the top of my head. It gives me that. So I can now substitute that in here. We get 5 to the power of 3 is equal to 5 to the power of n minus 1. Again, technically we would use a log. Did you guys use logs this year?
I've heard about what is.
Okay. It's just another algebraic representation of exponential functions. But here's an algebra trick. If you have two powers that are equal to each other, so the bases are the same, you can just drop the bases and just work with the exponents. So now the exponent is 3 is equal to n minus 1. That's a much easier question. We isolate for n. We end up bringing the 1 over, and we get n is equal to 4. And that pans out with exactly what we found. Our fourth term number was 750. Okay. Then with that being said, we got our sums. We have one sum and two. Well, why don't we sum up to the fifth term, just so we kind of have some values, because this can get exponentially large. And that's exactly what a geometric series is. It's an exponential growth type of question. Arithmetic is a linear type of growth. The only difference is linear and exponential are continuous, which means all the real numbers like decimals and fractions, they all exist in between. These are called discrete numbers. Discrete numbers is usually we only have set integers. Like, for instance, in this pattern, only 6 and 30 and 150 exist. We don't get the numbers in between because we're only working with those cardinal numbers. Not too important for what we're doing, but let's do our sums here. So let's jump over, put our two formulas here. We had 6, then we had 30, we had 150, 750, and then 3750. Let's get the sum of this. We'll take some stock of what we have. That's our first term, and that's our fifth term. That's going to be helpful. The sum formula, one of them says this: n plus 1 minus t1 over r minus 1. And the other sum formula is ARN. Let's see if I can remember that numerator. A and then times r to the n minus 1, I believe, all over r minus 1. Okay. Let's take a look at our two formulas. This one is asking us for the next term minus the first term. I don't have the next term. I could go and work it out, but that's a whole nother step. So this formula right here, I'm going to go, that's a whole extra step. Let me see if I can work with formula 2 to solve this, and then maybe we'll check with this one after. Formula 1, we're on the sum of the fifth term. So we're looking for the sum of the first 5 terms is equal to a, which is our first term. We know that's 6. The common ratio was 5. We're looking for the n value. Remember, we just replaced it with 5, so it's the power of 5 minus 1. All over the common ratio, which was 6 again. Oh, that's a lie, which is 5 minus 1. Hey, we were able to substitute in. So this is just algebra now. We're going 6, 5 to the 5. You got a calculator handy? Because that is not something I know. Did we get that at one point? I think we did in this question.
I think 3,125.
Thank you very much. And all of that, and that shouldn't be over 4. So 5 minus 1, which is 4. Okay. Can we do that number times 6 divided by 4? I mean, I might be able to reduce it a little. That could be 3 and 2. 2 doesn't go into that, so it's not going to be too helpful. It's going to be 1.5 times that number, whatever it is.
4687.5.
4687.5.
Yeah.
Oh, I think we've made an error in here somewhere. The reason I think we've made an error is we're adding up all these terms here, the sums of all these, and there's no decimal values. In fact, if we look at it, my ones column is a 0, a 0, a 0, a 0, and a 6. Okay, so I got some kind of error here. Let's make sure we did everything correctly. Let's double check our formula. A r to the n minus 1, r minus 1. Pretty sure that's right. Well, r is not 1. Yeah, that works out. Okay, let's check out how we plug things in. A value was 6. That's good. R value was a common ratio of 5. So that's 5 and 5. Subtract 1. Subtract 1. We were looking for the sum to the fifth term. 5 to the power of that would give us, double check that one. I know that 125 by 5 would give us 4. 12, 625, 2, 10, 12, greater 1, 3125. That's what we got there. Oh, I know. We calculated this. I forgot to subtract by 1.
Oh.
That one little thing made a big difference in our formula here. So that's good. I took your value. I forgot to subtract by 1. So now subtracting by 1, which would give me a 4. Now let's see if we can't get a better value here.
Oh, oops. 6 times.
I know that I could do this. 3, 2. And I could do
Okay, 4686.
4, 6, 8, 6. 6 in the ones column. That's making quite a bit of sense for us. Let's double check. We're going to use this one. So here's my trick to you is we need to calculate this. In other words, we need to take this value and multiply it by 5. Okay, I can do it by hand too. You want to calculate, I'll go by hand. 2, 3, 5, 7. Tell me if that number's right. 18,750. Yeah. Nice. We're going to subtract by our first term, which is 6. And we're going to divide by 5 minus 1. So 18,744. I always write a 4 in. I mean to subtract by 1. That's just my answer is 4. And then I do some division. It's going to be
Yeah, it's the same thing.
4686.
Yeah.
All right. So we've done it correctly. Good. So that's the idea with our geometric sequence. Okay? And just like I said before, they could ask us to isolate other values in the sums, but
It's
you have
just
two sums.
geometry.
Yeah, just one is like a type of exponential relationship, and the arithmetic is more of a linear relationship.